Hello everyone. The topic I'm presenting today is the Fronthauling for 5G LTE-U ultra-dense closed small cell networks. The main reference of this presentation is from the paper with the same title published in the IEEE Wireless Communication in 2016. Here is the overview of the presentation. I will introduce on the ultra-dense cloud small cell network, UDCS-net in short form, then elaborate on the cloud radio access network, its concept and the challenges in the front-haul links, followed by the elaboration on the candidate front-haul technologies in the 5G LTE-U UDCS-net, including the millimeter wave-based access link and front-haul link, the unlicensed spectrum access, and free space optical. Then I will compare the front-hauling candidates in 5G UDCS-net, followed by the conclusion. The UDCS-net is a promising technology to meet the requirements of explosive data traffic in fifth-generation mobile communications. It incorporates cloud computing into radio access network and involves massive deployment of small cells. The low-power small cells can improve the coverage and capacity of cellular networks because it will shorten the distance between transmitter and receiver. From the figure on the right, a UDCS net can comprise a macro remote radio head and many small ones, which can be deployed on each floor of a building or hotspot scenario, for example, in a stadium with ultra-dense devices. The baseband unit pool on the cloud can support heterogeneous remote radio heads, which are macro, small, and Wi-Fi remote radio heads. The cloud radio access network is an important part of the UDCS net. It will decouple the traditional role of the baseband station into two parts. The first part is the remote radio heads, which handles the radio frequency processing, and the baseband unit clustered as a BBU pool will provide large-scale baseband processing and management of signals transmitted or received from diverse remote radio heads, where the cloud computing technology provides flexible spectrum management and advanced network coordination. Through the front haul between the remote radio heads and the baseband units, the cost-effective and power-efficient remote radio heads can operate as soft relays by compressing and forwarding the signals received from user equipment to the centralized baseband unit pool. As the baseband signal processing of BBU is centralized, the CRAN can achieve high processing efficiency and consume less power. A prerequisite requirement for centralized processing in the BBU pool is an interconnection front haul with high bandwidth and low time latency. Unfortunately, the practical front haul is often capacity or time delay constrained due to massive deployment of remote radio heads and limited bandwidth. This will have a significant impact on both spectrum efficiency and energy efficiency. Basically, there are two categories of front haul. The first category is ideal without any constraints. A good example is the optical fiber communication, because it can provide a high transmission capacity, but at the expense of high cost and unflexible deployment. The second category is the non-ideal with constraints. The example is the microwave. It is cheaper and more flexible to deploy, but at the expense of capacity and other constraints. The current spectrum of the LTE cannot satisfy the requirements of ultra-dense small cell networks. Millimeter wave is an ideal technology to achieve high capacity in the UDCS net because it has large available spectrum, ranges from 30 GHz to 300 GHz, where the 60 GHz is more suitable for the 5G mobile communications, because there is a license-free or light licensed 9 GHz bandwidth available around 60 GHz. And the millimeter wave technology uses the narrow directional beam, which can enable the high spatial reuse. However, the millimeter wave links are susceptible to blockage. However, these issues can be resolved by multi-hop relaying, which we will discuss later. So, the millimeter wave can be used for the radio access and front-hauling in the UDCS net. The single-frequency operation can cause strong cross-tail co-channel interference, and the small cells can experience frequent handovers and cell changes. This issue can be alleviated by a phantom cell concept, which consists of a macro cell and small cells. In a phantom cell, the control plane and the user data plane are separated. The control information is sent by the high power nodes, for example, a macro cell, at a lower frequency, and the payload data is conveyed by a low power nodes, for example, the remote radio heads at millimeter wave frequencies. So, we need an efficient and effective small cell discovery scheme in the millimeter wave bands. Basically, there are two schemes. The first is to let the macro base station get the central control over the millimeter wave small cell discovery. In this case, the macro base station should know the supportable area of the millimeter wave small cells and track the motion of all user equipments. Whenever a user equipment enters the coverage of a millimeter wave small cell, it will notify the small cell base station and the user equipment for further connection. The second solution is to implement small cell discovery at sub-3 GHz low frequency bands. In this method, we need to choose a proper reference signal received power threshold to match the discovery area by the low frequency band with the actual supportable area in the millimeter wave band. The figure plots the capacity of the total access links in a UDCS net using 60 GHz millimeter wave communication, with the assumption given below the figure and model the path loss as the formula given here. From the plot, we can see that the capacity increases as the number of remote radio heads increases, because when the number of remote radio heads increases, the user equipment can find better remote radio heads to associate with using the maximum signal-to-noise ratio association rule. The interference between different users or cells can be neglected due to the use of directional beam. In a non-line of sight scenario, the remote radio head can connect with the baseband unit through an aggregation node by multi-hop relaying. The millimeter wave is used to link the remote radio heads to the aggregation node. There are two schemes for the millimeter wave front haul link. Depends on whether the access link and the front haul link share the millimeter wave spectrum. The spectrum of millimeter wave can be used more efficiently in the in-band solution than in the out-of-band solution. However, the in-band solution requires effective spectrum reuse plans, including the frequency division multiplexing, in which the access and front haul links use different spectrum bands, and the time division multiplexing, in which the access and front haul links use the same spectrum in different time slots. Here, we can see that the capacity performance for an UDCS net. We assume all user equipment are connected to the aggregation node with two hops, and the simulation settings follow previous access link capacity plot. From the plot on the right, we can see that the downlink system end-to-end capacity tends to be a stable value. The reason is first, the neighboring remote radio heads interfere with the user equipment with a long, non-negligible side lobe by using a directional beam, and the Shannon capacity formula follows a log concave feature. Fronthauling using unlicensed spectrum access. Wi-Fi uses unlicensed 2.4 GHz and 5 GHz bands with 500 MHz bandwidth. The listen before talk makes LTE works effectively with Wi-Fi. The figure below shows is from a Qualcomm technology. They introduce a more sensitive threshold that is common for all technologies when sensing each other, the energy detect threshold. So from the figure, we can see that if no signal is sensed based on the energy detected threshold, then we go ahead with the transmission right away. And if the channel is busy, detected by the clear channel assessment, then we wait for it to become clear first. Once it is clear, we wait for a random number of additional clear channel assessments, indicating that the channel has remained clear before starting transmission. The unlicensed spectrum used by Wi-Fi is a potential candidate for fronthaul in the UDCS net, because the operator does not need to purchase separate frequency for fronthaul, and the efficiency of unlicensed spectrum can be improved by reuse in both access links and fronthaul links. For the fronthaul from the remote head to the baseband unit pool, as well as the multi-hop links, free space communication is also a promising candidate, complementary to the microwave technology and the optical fiber in traditional cellular networks. The free space optical mainly has 4 advantages. First, it has a wide optical bandwidth. Second, the laser beam in the free space optical is directional, so it is inherently secure and robust to the electromagnetic interference. And the frequency band used by the FSO is above 300 GHz and is unregulated. And the fronthaul based on the FSO can be deployed and installed rapidly. However, the weather phenomenon can affect the performance of the FSO, especially in the thick fog weather. And for the millimeter wave, the rain weather will affect the performance because the raindrops are roughly the same size as the radio wavelengths, which cause scattering of the radio signals. So a combination of the FSO and the millimeter wave approach can be used to achieve both high capacity and link availability because of the combination weather of rain and thick fog is rare to occur. Now let's compare the fronthauling candidates in 5G UDCS net. The optical fiber and the FSO have the highest capacity due to their high bandwidth. However, the costs for them are also high. The cost we mention here is the equipment, installation, and the maintenance cost. The optical fiber and sub-6 GHz requires license, and the optical fiber and the FSO can be used for the fronthaul, where the rest can be used for both fronthaul and access links. Millimeter wave and the FSO requires line-of-sight communication, where the rest can have the line-of-sight or the non-line-of-sight communication. For the deployment, the optical fiber is the most difficult to deploy, followed by the FSO. Now let me conclude the presentation. The UDCS net combines the advantages of a cloud radio access network and ultra-dense small cells. In the presentation, we elaborate the advantages and challenges of various fronthauling candidates, and compare the difference between those candidates techniques. While the optical-based front-hauling techniques are free of interference, the infrastructure cost can be high. And for the RF-based front-hauling techniques, the ongoing challenges remains how to cope with the co-channel interference. That's the end of the presentation. Thank you for watching.